We do have a test on Tuesday, so a week from today. You have your review sheet to start working through. I didn't include vocabulary. And so I want to make sure that you are understanding all the vocabulary we've been talking about, that it makes sense to you. You know how to use it in a sentence. You know what its definition is. If you want to make flashcards, that's highly recommended. But more than just memorizing, I want you to understand its concept. And then Miss McGarry was gracious enough to stay after school on Thursday so that she could run a Pear Deck review with everyone. So she's in room 307, and I know some of you do have 7th period, so I'm going to make sure to publish the Pear Deck with some instructional videos for anyone who wasn't able to make that session, so you can still get that review. And then I'm hoping that a lot of you have started your Speed of Sound CER. But the Speed of Sound CER is due next class. So make sure if you haven't gotten it started, you get it started. I do have quite a few students who have turned it in already, which is good to see. But the CER is 25% of your grade, so this assignment is going to impact it.
This one CER is 25% of our grade?
No, this is in the 25% category. So because it's the first one, it's going to significantly impact it. But you want to continue. We're going to do more CERs.
Are we going to be able to do CER corrections again?
Yes, of course. You are going to be able to do corrections as well. So feel free to submit what you have. Wait for my corrections. I don't dock you. It's not like your test or your quiz. It's not like your quiz where you can only earn up to 70. You can earn full credit just by reflecting on your CER and making adjustments. Okay? Questions on any of this? Okay, let's go to the Speed of Sound because I know that I demonstrated a lot of these concepts to you, but it's a lot better when you can experience it. And the first one I want to go into is the warm-up that we did in class. And so the warm-up was related to when you have two tones that are close in frequency, Chase, then you should hear something that we call a beat. So I have a tone generator that has 440 and 442. They're really close in pitch. And this is as loud as I can get it, unfortunately. But I'm playing them at the same time. Can you hear that? I should have been a singer. Why I chose physics. Can you hear that beat sound? The interference of constructive and destructive tones? Yes or no?
Yes.
Okay, good. Okay, I'm going to turn this off. Okay, the other thing I wanted to show you is beats don't just happen when you have different frequencies, but they also happen when you have the same frequency or the same tone played from two different positions. So I've got two speakers. They're going to play the same tone. I'm going to play a C. At least Miss McGarry told me this was a C. On my frequency generator, and I want everyone to stand up. I want you to walk around and try to find points of destructive and constructive interference. And when you find one, raise your hand. Was anyone not able to hear a change in tone or amplitude or loudness? Okay. This is something we don't perceive because generally we don't listen to anything that is one tone and only one tone for a long period of time, right? We might have speakers in our homes that are surround sound and are in different places in our room, but when you have changes in amplitude or volume and changes in tone and notes, then you don't perceive this interference as much as if we're listening to one tone and only one tone for a significant period of time. So a few things that I want to talk about with sound interference. Most of this is review. is sound interference is a wave interacting with its reflection. I didn't talk about this as much, and I am going to test you on this. But the reflection, if it hits a fixed point, is always going to invert, meaning it's going to reflect back and flip to the other side of your equilibrium point. Okay? As it does that, you get a crest and a trough lining up with each other to create constructive interference, the maximum amplitude and minimum amplitude interfering with each other constructively. And then this is more for your quiz today. We've done our warm-up on the two open ends, but when you have one open end, the fundamental harmonic always has to start with one antinode and end with a node, the least amount you can fit into your tube. And then when you have two fixed ends, a scenario with two fixed ends would have to end in two nodes, the least amount of nodes you can fit into a two fixed end medium. And so this is the fundamental frequency or the first harmonic for each of those types. And then as the speed of the wave, or as each harmonic increases, the speed of the wave doesn't change because it only depends on the matter that the wave is traveling through. And the air stays the same, right? The density of the air is not changing. The wavelength depends on the length of your matter, the length of your tube, or the length of your string. And so your fundamental frequency stems from this length. And then last but not least, your frequency is a multiple of that fundamental frequency, just like what we did in our warm-up. 202 became 404. What would the third harmonic frequency be? 808? 606. It's always a multiple, so third harmonic is 606. Fourth harmonic is 808, 909, 10, so on and so forth. Question?
Would you not do like a one open end harmonic, or would you go just like 1, 3, 5, you would have to go
It actually is 135 when you have a one open end, so I would stick with 135. Okay. So this is pretty obvious. But what I want you to understand about sound intensity is it's not just loudest when you're closest to it, but as you move backward, the sound intensity, the loudness decreases, so they're inversely proportional, but they're inversely proportional by a radius squared. So it's an inverse squared proportion, okay? So the closer you are, it's exponentially louder. The further away you go back, then it starts decreasing by a factor squared. This is due to the fact that, as I stated earlier, sound emits in a three-dimensional manner. So it's emitting energy, because that's what wave is. Wave is energy being transferred out into a spherical area. The amount of energy that's transferred is the same. So if you spread that energy out 10 meters, it's going to be loud. If you spread it out 20 meters, it's going to decrease in intensity by a factor squared, so by 4 times. And then if you go out 30 meters, it's going to decrease by a factor of 9. So you want to think about the inverse proportion.
So that means
So intensity doesn't necessarily. Yeah, intensity does not affect the frequency. It only affects the amplitude. So this is the amplitude, which affects the loudness of your sound. Any other questions? The units, you know what? This one would probably be watts per meter square. but I'm not going to have you do any actual calculations with intensity, just understanding the concept of inverse squared. Any other questions on this? Okay, the next thing I want to let you know is the fact that not only distance, but as we experienced just a second ago, the position that you're in when you have two speakers interacting or two sound waves interacting, the position, even if you might be the same distance away, the position is going to affect how loudly you hear that sound. So if this person, even though they're standing the same distance as this person, they're going to hear constructive interference versus this person who's going to hear very, very low volume, and this is really high volume. And that's exactly what you are hearing when you are moving back and forth and you're like, whoa, it's really quiet and now it's super loud. So depending on your position, no matter how far away you are, it could affect the sound as well. So I'm going to skip all these concepts here. I did want to do a demo just to show you. You were supposed to do this, but I'm going to simulate it for you just so that you can see what intensity looks like graphically and also what constructive and destructive interference look like. So I'm going to start with one sound wave, only one. And this is going to measure its amplitude, which is pressure. The closer I am, and let me dim the lights so you can see it a little bit better if I dim the lights. So there's a gray graph that you're going to see when I'm closest. Look at how big that amplitude is versus further away, the amplitude is smaller. And I know it's hard to see this square sphere, the lighter one, but it's moving up and down because of the high intensity, the high sound. Now, if I were to turn the other sound wave on, and now we've got interference, I can move this sound wave, even though it's closer to the speakers. Notice how its amplitude is a lot shallower. It's a lot more quiet here than it is for this person, even though this person is closer to the speakers. And it's because he is sitting, or she is sitting in a position of destructive interference. So when you look at these spheres, the points where the waves are pretty clearly black and white, that's your constructive. The positions where it's kind of faded out, where the waves are interfering with each other, that's destructive. And you can see destructive and constructive right here. Is it? Can you see that tiny gray dot? Not at all. Yeah. You can see it a little bit. Okay, the other thing I wanted to show you is the particle view, because a lot of students think that waves or sound can transmit matter. But these are the particles in the air. They're moving, but as the sound wave moves out, do the little particles move out with it? No, it just vibrates. So these particles are not moving with the medium, these particles in the medium are not moving with the wave, it just vibrates as the wave passes. And that's a common misconception. A lot of students think that in an ocean wave, the ocean wave can pull you to land, but an ocean wave is not going to pull you to land. You need wind to pull you to land. So anytime you see maybe trash being washed up, it's more due to wind rather than the water wave itself. Anyone surf here? Used to. So surfers, you'll see them bobbing up and down on the waves out in the ocean. It isn't until they use their body's energy to kind of paddle them along with the wave itself that they're able to kind of ride the wave. But you need to exert your own energy to get on that wave versus the wave carrying you with it. And that's because matter doesn't move when wave travels through it. It doesn't move along with the wave anyway. Okay, the other thing about sound waves that's really interesting, is a common misconception that people experience when they watch sci-fi movies. So here's a sci-fi movie of an explosion in space. So sound without a medium because space has no air.
Never leave an enemy stronghold intact. Major Scott was one of your father's first rules of engagement. That is a direct order. I hate spoilers.
Okay. Is that realistic? If you were in outer space, would you be able to hear things blowing up? What?
Like just hit you.
It would hit you. Definitely. You'd feel the energy. You might feel that heat, but you definitely wouldn't hear it. It is silent in outer space.
Say theoretically, you could be inside of those positive explosions without being hurt. You would hear it, right?
If you were inside a, like in a spaceship, just like what they were in, where you had air within it, you need air particles is the key. And so because space doesn't have air, you're absolutely not able to hear a thing in outer space. Now, here's a demo if you don't believe me. What this person did before I play it is he has this bell jar that can suck air out, and he included not just a alarm to create a sound, but he also included the microphone. Because a lot of people think that as air sucked out, maybe the sound is contained within the bell jar, but because the microphone is in there, you'll be able to hear what sound is happening within. So I'm going to play this video for you for what actually happens in a vacuum, or what we call no air, a no air location or space.
I've got a vacuum pump, a bell jar, an alarm, and a microphone to demonstrate that the sound level will drop in the vacuum. So let's set up the experiment. We're going to place our radio microphone into the bell jar and set our alarm. When the alarm goes off, you'll hear it. It'll be very loud. Okay, I think I can just about hear that, but you'll be able to see on your screen a visualization of how loud.
So dB, decibels, which is what you read about
from the bell jar
in the physics classroom and textbook.
So that the air can't get in, and open this valve to allow our vacuum pump to suck out the air. The air being sucked out now, and you should see the sound level dropping on the microphone. So you can see our gauge reads 0, and also the levels on the microphone have completely dropped. That's because a sound source vibrates, and that pushes the air and transfers the vibration to you hearing it. But because there's no air in our vacuum, the alarm is vibrating, but it can't transfer that to the microphone. So I'm going to do the reverse now. I'm going to shut this valve and then open this valve. So the air's back in now, and the microphone's picking up the sound, and I can just about hear it as well. So that's been our experiment. We've proved that sound cannot travel in a vacuum. If you are going to replicate this experiment, please have an adult present. Thanks for watching.
Just in case you wanted to, you know. So the other thing I wanted to point out is there are waves that can travel without a medium. And we're going to talk about it in our next unit, which is more a subunit of waves, which is the unit of light and the electromagnetic spectrum. So electromagnetic spectrum or electromagnetic waves can travel through space, places where there are no mediums. So if you notice, you could see the light emitting from the explosion. That's true, because light can travel without a medium. So So can microwaves, ultraviolet rays, X-rays, those are all examples of electromagnetic rays. The mechanical waves, like water waves, earthquake waves, and sound waves, need a medium to travel, and we call those mechanical waves. So we talked about sound waves as a longitudinal wave. There's another wave that I haven't touched on, and this is our last topic of discussion.
I've got a vacuum pump.
It's earthquake waves. So the interesting thing about earthquake waves is that it can be both longitudinal and transverse. So those are P waves, which are longitudinal, meaning the medium travels in the same direction as the wave itself. And the S waves, it makes an S shape because it creates a transverse shape, right? You can think of transverse waves as S shapes. That is your wave where the medium moves perpendicular to the wave speed. So S waves and P waves are the ones I want you to learn for the test. The other two aren't going to be tested on, but waves actually travel in something called a love wave. It's like a transverse wave where the perpendicular motion of the particle is it's perpendicular to the wave speed, but it moves left and right in a love wave versus up and down. And a Rayleigh wave is a combination of longitudinal and transverse. It actually pulls the wave particles up and down, but also left and right to create this circular motion. And that's also what you see on the surface waves of ocean waves. It's more circular Rayleigh wave types rather than just transverse or just longitudinal. But don't worry about these two. I want you to memorize that P waves are longitudinal, S waves are transverse, because transverse waves make an S, right? So, good way of memorizing that. The other thing I want to ask is, which of these earthquake waves do you think travels faster? Which one do you think will travel faster? Alex? The longitudinal P wave is going to travel faster than the S wave. Vincent? Transverse, was there a reason?
I changed my mind. I realized that it's not sound.
Yeah, it's not sound, and sound is the only exception where high density means fast. For all other waves, longitudinal waves are going to move faster than transverse waves, and I'm going to show you a demo of this here, where you've got the the longitudinal P wave traveling first, the S wave following. Observe, I know this is an animation, but observe what happens to the motion of these houses. It's a really big house. Okay, so here's where the epicenter of the earthquake is. It starts here, and as it travels forward, the longitudinal wave is moving this way, or your P wave, and so it moves it up and down. S wave is transverse, so it moves it left and right. So notice how the surface waves are the kind of rotating wave, but waves always travel in sets of P, then S, and then your Rayleigh wave, or your rotating type of wave. So it'll shake your house and any other structures in upward fashion, left and right fashion, and even around in a circle. So the reason why you want to learn about this is because it really affects the structures, especially since we live in California, the way the structures in California are built versus other places where there aren't earthquakes. You're going to be doing an engineering lab, and I want you to think about those concepts when you engineer your little model of a house encountering an earthquake. So this is the Los Gatos Loma Prieta. I'm presenting this because it kind of hits close to home, right? You might have parents that were in this earthquake and experienced it. This is the damage that was done to properties in Los Gatos. And if you look at this color scale, the red is the fault line, and it was reddest right in the Los Gatos area. So just see how the energy of this wave travels and the intensity of the wave as it hits. So it starts here. The fault line is right around here, and it extends down. But it's darkest right around the Los Gatos area.
So pulse myself the sound very small. How do they get such accurate?
All of this data is used through, I should have shown it to you, but there's a Richter scale. And I think they just have them stored at different facilities, and it measures it. They also are able to measure the intensity and then kind of calculate the distance between different points. Question. What? Yeah. Okay, so I've got other visuals of different waves. These show you kind of the scale of intensity. What I want to highlight, though, this is the Hayward Fault. The Hayward Fault's what we call a creeper fault line because it doesn't necessarily, although we're projected to have a earthquake from the Hayward Fault soon, but it's more the type of fault line that obstructs like structure over periods of time. So in 1971, it was affecting this curve right here. 1974, you can see how much more it's displaced. 93, 2005. So that's what we call a creeper fault line. But all that pressure that's causing things to kind of slowly move could end up building into, they actually predict a 7.0 earthquake from this Hayward fault line to eventually come.
That's a big one.
It's a pretty big one. Now, what I want to show you in the next slide is the fact that our structures, so this is an earthquake 6.7. This was in 1994. And this was the damage that was done from that earthquake. So all these structures kind of broken down, bridges falling. This was damage done to a building. It still held up pretty well. The stairways fell over. But this is an earthquake. 7.0 is not that much greater than a 6.7, but in Haiti, an entire building from top to bottom was basically, you have to break that down and start from scratch. Whereas in the previous slide, this one was still pretty intact except for a few structure pieces falling apart at the base. So compared to a third world country, you can see how the way we build structures in California versus Haiti can make a big difference, right? So here's Haiti, a 7.0, California 6.7. I mean, everything they have to start from nothing. Here, we can probably rebuild some of this structure and keep the main building. But the last slide I'm going to show you is focused on how we build structures here in California and all along the West Coast to ensure that we don't have anything like this. So, any questions before I play our last video?
Yeah,
What? It is logarithmic. Yeah, I didn't want to get into too much detail on the Richter scale, but yeah, that's a good point. Okay.
So that means that the, I guess, Hayward one would be 10 times as much as the other one. No, the other one's like 7.8. This one's like 6.7.
I'd have to. Yeah, I have to compare what the actual values are. Logarithmic means by a factor of 10. But let me think about that. How the difference plays from one variable to the next. To the 10th power, right? Yeah. So a 6.7. Let me do a little calculation. I don't want to try to think of it off the top of my head and give you something valid, but it's a value to the 10th power difference between one decimal to the next.
I was talking about compared to like that Hayward Freeman.
Yeah, between the 6.7 and the 7.0.
So if you go back a slide.
Oh,
That's a Hayward one.
oh, I see, the 7.0.
Yeah.
So the 7.0 here, this one was, when was the last, I think this was years ago in the 1900s. So how it decimated this home would be different than the way we build houses now. One video I want to show you before we start our quiz, and it's a really short one, is going to help you for your engineering project. You're going to build a building out of pasta, and you're going to use techniques you learned from this video to build a good structure. I actually have a shake table. I know it's hard to see, but I'm actually going to shake with low frequency, a little bit higher frequency, get higher and higher and higher, and so we're going to see which structures actually hold to the shake table, and it's based on your design. And I'll go into detail in that next class. But I want to give you some ideas before you leave, so let's do one more video and then we'll take our quiz. Oh, you need volume.
In the region in over 80 years. It killed 63 people and injured nearly 4,000 when sections of bridges failed, buildings collapsed, and freeways buckled.
He's talking about Loma Prieta, right here.
$6 billion. And geologists tell us future quakes are coming. It's not if, but when. What can we do to make our buildings and bridges safer before the next big earthquake hits?
The simulation of earthquakes is a big part of what we do.
Khalid Masalam is the director of the Pacific Earthquake Engineering Research Center, headquartered at UC Berkeley, with testing facilities in Richmond, California. To test how different structures respond to the complex forces of an earthquake, the center's research engineers rely heavily on a piece of equipment called a shaking table. Engineers use this shaking table to simulate real earthquake conditions on just about any structure that they want to model.
The shaking table is one of the hallmark pieces of testing equipment that we have. It's 20 feet by 20 feet. It's made of reinforced concrete so that the table can be very stiff.
Beneath the table are mechanical devices called actuators that, working together, can simulate an earthquake. 2 actuators shake the table along the x-axis, 2 shake the table along the y-axis, and 4 shake the table vertically along the z-axis. Additionally, the table can also rotate independently along each of these 3 axes.
Those all represent the P.S. Rayleigh and Love wave.
Of these recorded motions from past earthquakes. And we have a computer that is connected to the table, that derives the table. And in this computer, we put the exact signal that was recorded in that particular earthquake in a digitized form.
If the table is clear, Clement Bartis oversees most of the tests performed on the shaking table. Companies often come to him to test how their equipment will perform during an earthquake. Today, a company is anxiously waiting to see how their new concrete line tanks stand up to an earthquake. 2 different scenarios are being tested. On the left, the wine tanks are freestanding on the shaking table. On the right, the tanks have been bolted down. In the control room, Clement dials in a simulation of the 2014 Napa earthquake. At first glance, it may appear that bolting down the tanks is the way to go, but upon closer inspection, Clement finds a crack at the base of the wine tank. The best method to secure the wine tanks will need further research.
We observed very satisfying behavior when we simply let the whole stack rock. And it leads to that idea that maybe it wasn't a good idea in the first place to bolt these units down, and maybe they are behaving better if we simply let them rock.
Letting a structure rock has actually come to be one of the most effective methods of protection from earthquakes. In fact, one of the most significant developments to come out of testing on the shaking table is the proof of concept for energy dissipation devices.
Basically, it's something that takes the accelerations or the energy from one source and basically dissipates it so that the impact of the earthquake to the building structure itself is minimized.
The building may sway and even develop small cracks, but major damage is avoided.
This technology is used very commonly now, 30 years after the original testing was done in the early 1980s.
In 1999, San Francisco City Hall was retrofitted with these devices. A year later, the International Terminal at San Francisco Airport was one of the largest structures in the world to be built on base isolators, a kind of energy dissipation device. Still, in earthquake-prone areas like California, there are thousands of structures that won't be able to withstand the next big earthquake. But with the help of the shaking table, engineers have more tools than ever before to protect against earthquakes, both large and small.
All right, so things to think about when you start building your model of a house out of pasta. That's what we're going to do next class. So work on your review worksheet at home because we won't have any time to do any review in class. We're going to be focused on building our models. Like I said, a review session, if you wanted to, will be on Thursday during 7th period. And then if you can't make it, I'll post the review pair deck.